Bayesian Statistics, Bayes Theorem example. So here's all the formulas we have up to now, minus Bayes Theorem, which I've stuck on the next page. But notice we've really progressed through defining lots of rules of probability, and these rules are all going to start paying off massively here in the next couple videos. Because they allow us to calculate probabilities on quite difficult structures and quite difficult problems, and they're going to allow us to keep this notion of probability around in many, many, many other sort of environments. So keep that in mind. All right, so let's get rolling here. So as you remember, here's Bayes' theorem. I'm not going to read it off again, but we have some sort of partition here in the denominator that goes along with it. Okay, so most people are familiar with what a phone is, and a phone manufacturer is interested in the quality control on microphones from their suppliers. They have 4 suppliers that supply these microphones, A, B, C, and D, and they know that A supplies about 23%, B supplies about 12%, C supplies about 42%, and the rest come from D. From past experiences, they know about 2% of the microphones are defective from A, 6% defective from B, 1% defective from C, and 3% defective from D. So, here's the question. A phone is returned from a store, okay, because you're a manufacturer, the store sends it back to you, for having a defective microphone. What is the probability the microphone comes from each of the suppliers? Not interested in just one, we're looking at each of them. All right, so let's start writing down what do we know. Okay, this is always your first step whenever you're doing these kind of questions. Just say, well, what do I know? All right, so let's start this off. The probability that the item comes from supplier A is 0.23, right? This says 23. We have the probability of coming from B as 12% or 0.12. Probability that it comes from C is 0.42. And then it says the rest come from D. So it didn't actually tell us what it was. It did tell us that 2% are defective from A. It told us that 6% are defective from B, and 1% is defective from C, and 3% are defective from D. So this is everything that the problem tells us. Now, what we need to do is we need to finish this out because we have A, B, C, and D here, but we don't have a probability of D up here. But we can get that relatively easily, right? We can use the complement rule because that's what we're interested in. The probability of D is 1 minus the probability of D complement. Well, what's D complement? Well, remember, A, B, C, and D form a partition of all the possible suppliers. So I can just subtract off each of those probabilities. So it's the probability of A minus the probability of B minus the probability of C. You plug all this stuff in, and you get that D is about 0.23. So I can add this up here to my list of things I know. Now, let's start with Bayes' rule. We're going to start with A. So what's the probability that the microphone came from A, given we know it's defective? Well, here I've listed out Bayes' theorem without using the summation notation, so you can see all the pieces in it. And that's partially what I'm trying to do is illustrate these pieces so that you can keep yourself together. So now it's just a matter of plugging in numbers. 0.2, which is the probability defective, given A, times probability of A right here. So 0.02, 0.23. Got that right in the numerator. And then I just go through and just basically pair these up all the way down and sum them together. Now, it's really helpful to just keep this number around because this denominator is going to be the same across all of these, okay? Because I'm looking at A, B, C, and D, and that's not going to change on any of these, the denominator. So when I multiply the numerator together, I get 0.0046 divided by 0.0229. Okay, and this is the number I'm going to keep around. That's equal to 0.2008. Okay, so did the probability change? Yeah, kind of, right? Because we know that A supplies 23%. Before we started, we would say, well, if I just had to guess, it would probably be A would be 0.23. All right, so moving on here, B. So I go through B, now I have the probability defective given B times the probability of B. Sorry I shortened the defective down here, otherwise it would fall off the page, but I'm just trying to keep it sort of readable at the moment. And if you notice, the denominator is exactly the same, and I just pull out the second piece and move it to the top. I get 0.0072 over 0.0229, which comes out to 0.3144. Okay, so that is very different than what I would originally thought, because I know that about 12% come from B. If I didn't know it was any better about this other information, that would have been my guess. We can go on to C now, and now I'm storing the answers up here as I go along, just because we're going to need them later. So when I do C, again, I just take what I had before, 0.0042 over 0.229, and that comes out to 0.1834. Okay, now, instead of going through Bayes' formula again, I can use this complement rule again. Subtract them all off like I did at the beginning and get 0.314. So here is the final answer that I would get. So I'm not interested in one of them. I'm interested in the entire probabilities across all the groups. And if you notice here, this is, it adds up to 1, just like it should. And that most likely came from B if I look for the one that was most likely to come from. And the next one would be D. C is pretty rare, and A is a little bit more common. All right, so this is how you sort of work with these Bayes theorem problems. They're a little bit complicated, and or tedious is what I would say, but they're really not that bad, because it's basically write down what you know, put things together, and then it's arithmetic. All right, so here's our formulas again. Bayes theorem still not on here, but in the next video, we're going to start talking about random variables, and we're going to talk about probability distributions, and then after that, everything that we do is going to be from a Bayes theorem perspective, or a Bayesian statistics perspective. But we couldn't have gotten to there until we go through this. All right, so we'll see you in the next video.